Can you imagine a world without Google Maps? Or sending an email? The technology doing it all, the computer, has roots stretching back thousands of years. But the leap from simple counting sticks to complex AI was hardly smooth. It was filled with revolutionary genius, wartime desperation, and moments that truly changed humanity forever. Believe it or not, the need for efficient counting is far older than any transistor circuit. Long before gears and vacuum tubes, humanity was already inventing ways to tackle big numbers using nothing but sticks, beads, and clever geometry. Perhaps the most enduring symbol of this ingenuity is the abacus. These marvelous devices have been used successfully for thousands of years across cultures from ancient Mesopotamia right through China. They were ingenious tools that allowed people to conduct sophisticated arithmetic while carrying immense amounts of information in their minds. However, as mathematics grew more complex, simple beads weren't enough, and modern mathematicians needed mechanical assistance. Fast forwarding a few thousand years, we find genius like John Napier battling massive calculations involving logarithms. He developed what are now known as Napier's bones, simple wooden calculation aids that dramatically simplified multiplying extremely large numbers. These tools demonstrate a crucial truth. The fundamental drive to quantify and simplify complex problems is not a technological invention, but an enduring, deeply human impulse. Before the vacuum tube and the microchip, computation was an act of elegant clockwork. Imagine a world where advanced mathematics wasn't done purely with pen and paper, but could be orchestrated by gears and levers, a mechanical dream made real. This age kicked off impressively in 1642 when Blaise Pascal designed his calculator, known as the Pascaline asterisk. It was revolutionary because it proved that complex arithmetic, things like addition and subtraction, could actually be mechanized for human use. Following him, Gottfried Leibniz built upon this foundation with an even more sophisticated machine capable of multiplication and division. These early devices weren't just novelties, they were serious tools designed to automate the tedious burden of calculation. They demonstrated a profound shift in thought, that abstract mathematical logic could be translated into physical, mechanical operations. The very idea of building intelligence through pure mechanics marked the crucial turning point away from human effort and toward automated thinking. But before electronic circuits or glowing screens, there was a man named Charles Babbage. This 19th-century English mathematician conceived of something so revolutionary that we only now fully understand its power: the analytical engine. It wasn't just an automatic calculator. It was a conceptual masterpiece, effectively laying out the blueprint for modern programmable computing itself. In his time, mechanical calculating machines were common, but Babbage envisioned a general-purpose machine, one capable of handling logic and any sort of calculation simply by feeding it instructions, or programs. While the massive difference engine he designed initially focused on crunching numbers via polynomial functions, it was the analytical engine that showed the full scope of his genius. It incorporated concepts like input via punched cards, followed by a central processing unit, or what we'd now call the CPU, and memory. Sadly, due to funding issues and the sheer complexity of building such an advanced machine with 1800s technology, the analytical engine remained mostly theoretical during his lifetime. Yet, his foundational work provided the intellectual jumping-off point that spurred future generations from pioneer Ada Lovelace to the inventors of silicon chips. As the world careened into World War II, the need for computation went from purely theoretical to absolutely critical, a desperate necessity that forced brilliant minds to build machines far beyond anything previously imagined. Before electric computing, even advanced calculations were agonizingly slow, relying on mechanical gear systems or human hands. Enter the vacuum tube, a pioneering piece of technology that finally allowed electrical signals to be manipulated with unprecedented speed and power. This period gave birth to colossal calculating beasts like ENIAC, the electronic numerical integrator and computer. Finished in 1945, this machine was massive, filling an entire room and requiring immense amounts of power, but its sheer capability signaled the true dawn of the electric age. Programmers like J. Prosper Eckert and John Mauchly were tasked with creating something that could process lightning-fast calculations for artillery firing tables and ballistic trajectories. While these initial machines were gargantuan behemoths, relying on humming vacuum tubes that heated up and occasionally burned out, they proved a transformative principle. Computation no longer needed to be slow or purely mechanical. It was fundamentally electric. This monumental breakthrough effectively launched the entire industry we know today, establishing the core methods of digital processing for generations of inventors to follow. But if the vacuum tube represented brute power, massive machines that required dedicated cooling and generated incredible heat, the next development was nothing short of miraculous. Enter the transistor. This tiny semiconductor device, initially demonstrated at Bell Labs in 1947, fundamentally changed everything we understood about electronics. Suddenly, engineers had a way to build complex computing circuits without occupying an entire room or needing an auxiliary power plant running just to keep them cool. The sheer drama of this miniaturization cannot be overstated. It was like upgrading from an early steam train to a sleek commuter bullet. By replacing those fragile glass bulbs with microscopic semiconductor junctions from materials like silicon, the cost plummeted and reliability soared. This breakthrough allowed computing to move out of highly secured government bunkers and into research universities, fundamentally democratizing access to processing power. It signaled that the enormous, custom-built machines of the previous decade were an artifact, making room for a whole new era of electronics we now take for granted every single day. If early computers were enormous room-sized beasts housed in steel cabinets, the next revolutionary breakthrough was something that shrunk everything down to the size of your fingernail. This was the integrated circuit, or IC, a concept that fundamentally changed our relationship with technology forever. Before the IC, building complex electronics required thousands of individual components, each wire and resistor soldered painstakingly by hand onto a bulky circuit board. The genius idea, pioneered independently by figures like Jack Kilby and Robert Noyce, was to etch everything needed, all those transistors, resistors, and connections, directly onto a single slice of semiconductor material, silicon. This groundbreaking consolidation meant that instead of miles of wiring, we could use one elegant piece of wafer-thin material to power an entire system's logic. Suddenly, the colossal complexity of modern computation became feasible for something small enough to sit on a desk, rather than requiring its own dedicated building. The ability to build powerful, reliable circuits so densely and cheaply is what finally moved computing out of specialized military labs and into our hands, setting the stage for the personal computer revolution we know today. For decades, computers were behemoths, rooms full of blinking lights barely accessible outside government labs or massive universities. But everything changed with a tiny chip, the microprocessor. These miniature processing units allowed computing power to shrink exponentially, finally giving us something portable and affordable enough for our homes. The real tipping point, however, wasn't just the speed, but how we interacted with it. Graphical user interfaces, pioneered by Apple's Macintosh in 1984, were revolutionary. Suddenly, instead of requiring arcane commands typed onto a black screen, users could click on icons and move a visible cursor, a concept as intuitive as using a modern mouse. This shift was profound. Computing moved from being specialized intellectual labor to something usable by anyone. The machine stopped feeling like an exotic tool for experts and started feeling like an extension of the person operating it. It's this blend of microprocessing power and user-friendly design that finally pulled the computer out of academia and right onto our kitchen counters, changing how we work, learn, and connect forever. But the true revolution wasn't in processing power alone, it was in connectivity. This shift began with ARPANET, a Defense Department experiment that first linked computers across academic institutions. What started as a packet-switching project designed for reliable communication gave birth to the concept of networked computing. When rudimentary emails and file transfers became routine between Stanford and UCLA, humanity realized they had stumbled upon something massive in scale. The adoption of TCP/IP by Vinton Cerf and Robert Kahn provided the critical standardized language, the protocol, that allowed disparate networks to speak to each other. By truly opening these gates, the humble academic experiment transitioned into the Internet, rapidly moving beyond military or governmental use. Suddenly, information flowed across wires and radio waves with a speed that was astonishing, transforming global commerce, sharing knowledge instantly, and knit together millions of people in a way previous generations could never have imagined. It was truly the birth of our modern, interconnected world. The history of computers isn't just about faster processors or bigger screens. It's the story of accelerating human ingenuity. Each device was merely a tool, a physical extension of our desire to solve problems and connect ideas. The evolution continues, reminding us that the next great breakthrough is only waiting for the right curiosity to point at it.